Okay, so this is what we were talking about. We were talking about how to generate electricity, and we said that if we move a wire in a magnetic field, we developed this expression for EMF, which was velocity times magnetic field times the distance h that the electrons move. Then we said that in order to calculate the EMF, you must integrate around the loop. And in order to calculate the work done, you follow one charge as it moves around the hoop. Then we also talked about this, which is called the flux rule. And the flux rule says that the EMF that is produced for motional EMF, the rate of change of flux causes the EMF to be produced. Now, if we have only one loop, the EMF produced looks like delta phi over delta t. But if we have more than one loop, say we have n loops, the flux rule will be rewritten as times n. And that's the magnitude. So I'm just talking to you about magnitude. There should be a minus sign here. Actually, no, let's not talk about the magnitude. Let's just put the negative sign here, because that negative sign is going to be important pretty soon. Okay, so Faraday was doing a bunch of experimentations with magnetic fields, with electric fields, and how those two relate to each other. So one of the things that Faraday did were these. Number one, for his experiment 1, he pulled a loop of wire through a B field, and he observed that this produced a current in the loop. Number 2, he said, what will happen if instead of moving the loop of wire, I actually move the magnet? So experiment 2, he kept the loop of wire at rest, but instead moved the B field. What did he observe? He observed that this also produced a current in the loop. Experiment 3. Then he said, what happens if I keep the wire and the B same, but I actually vary the strength of the magnetic field? What will happen in that case? Okay, so I keep both magnet and loop stationary, but instead change the strength of the B field. What do you think he observed?
Probably more current.
He observed the same exact phenomenon. Why isn't it letting me paste? This also produced a current in the loop. So this led him to say that no matter what the reason it was that the B field was changing, regardless of how the B field changed, there will always be a current that's produced. Okay? So he said, he generalized all of this to say whatever and whenever the magnetic flux through a loop changes, an EMF equal to negative n d phi over dt appears in the loop. Okay, so we call this the Faraday's law. And most people, you will see this written as a changing magnetic field induces an electric field. Okay, and it's mostly written as E dot dl equal dB over dt dot dA. In integral form, or written as del cross E equal partial B over partial T in differential form. Now, this seems like it's something new that I have introduced you to, right? But look at it carefully. It's actually something that you have seen before. And I'll show you how this develops. Okay. Are you ready for this? It's a little bit of math. I don't think Griffiths does it, but it's actually very simple. And you should see it once so you know it's not nothing new, right? It's something we've seen before. I've introduced it to you before. Ready? So again, it won't seem like a black box. It'll seem like, oh yeah, that was easy. Okay, ready? Here it goes. I told you in chapter 2 an equation that I call the ED equation from chapter 2. Do you remember the ED equation? V equals ED. That's the same Ed equation. V equals ED. Where now, because we have a changing DL, we're going to use a loop. Okay, it's the same equation. Now, what does the flux rule say? I can write for E. Partial negative d phi over dt. Imagine I only want to do it for one n, and then we can, substitute it. Okay, so I'm going to do it for one n. So may I write this as do I also know that magnetic flux, oh, why is it so thick? Oh. That magnetic flux is nothing other than BDA or magnetic flux is B dot dA. May I plug that value into the above equation? Will I get may I rearrange this as integration dB over dt dA integration E dot dL? So one side is being integrated over dA, the other side is being integrated over dL. Okay, do you remember what the Stokes theorem was? And it's okay if you don't. I can use the Stokes theorem to rewrite this as both sides integrated over dA. May I rewrite this as negative dB over dt is the curl of E. Isn't that what I wrote here? So it's technically not new. We have just written our Ed equation, now introducing a B field in it. Now let's concentrate on this equation. What is it telling me? It's telling me that when I have a changing magnetic field, it produces an E field, and there is a curl of that E field that exists. And it exists only as long as there is a changing magnetic field. So it doesn't mean that all B fields will create an E field, right? It only means when the B field is changing somehow. It could be changing when I move the loop. It could be changing when I move the magnet, or it could be changing if I change the field strength of something, right? In all of these cases, it produces the E field. Do you remember our discussion from yesterday where we were doing this, this thing? Where we said, what is the force that's causing the electrons to be pushed? And we said that that was called the electromotive force. This produced E field, do you remember me writing this down, that this is where that E field comes from? That or this? Do you remember that? That's what's causing the push that causes the electrons to flow. And it's only flowing until the B field is changing somehow. Got it? Okay, so these are all connected. And that fascinates me because it's just so amazing that people look at this equation and they tell you to memorize it, but you don't really know where it came from. And it's so simple and so fundamental a concept, right? All it is as long as there is a B field that's changing, there will be a curl of E present. Do you remember in chapter 2 when we were doing electrostatics? We said that curl of E is 0. Now curl of E is not 0, but only in the presence of
a B field.
A B field that's changing. So B field could be there, right? It still will not. So imagine if there was a B field here and I would put a wire in it, nothing will happen. What do I have to do? I have to move the magnet. Does that make sense? And fundamentally, that's all what all power plants are doing. They're basically big magnets, and they move those magnets to create electricity. It could be due to
like
water,
sound generator,
or water flowing down an incline, right? All it's doing is moving those turbines to move the magnets to create electricity. Actually, I think I have a really good example. Have you seen my example? I'm going to walk around and see. Yeah, here.
Is it the thing that you crank?
Yep. I'm going to show you. It's a thing that you crank, right? That thing. I'll try to put it here. Can you see it?
Yeah.
Kind of heavy. So all it is horseshoe magnets, right? And I'm going to crank this, which I don't know if you can see it, but you can see it from here, right? Can you see this? Yep. So all it's doing is it's moving the magnets, I'm basically moving this wheel, and there's a magnet inside here with coils, and that's being moved. The light bulb turns on. But it turns off as soon as I stop cranking it. The magnets are still there. Electricity is not flowing. Why?
It's because the B field's not changing.
It's because the B field's not changing. Now, instead, if I was somehow to take this coil and leave it there and move my magnets, can I do that?
Yeah.
Will the effect be exactly the same?
Yeah.
Yep. And that's what Faraday's law says. That's it. That is fundamentally what Faraday's law is. Isn't that so cool? And that's the basic principle for every power generator on the entire planet. Woohoo! It's not anything complicated. So fascinating, right? I actually really like this demonstration. It's one of my favorite things. So cool.